I'll start by saying a few words about classical chaos before we go on to quantum chaos. All right, so the basic question in classical chaos, we all know this. We start with some system and we slightly deform the initial conditions of the system. And then we evolve the system over time. And we check whether this small deformation led to an exponentially large deformation at large times. If it did, we call this the chaos exponent. The other exponent, and we call the system chaotic. A basic question in classical chaos is what happens if we start with a system that's not chaotic and add interactions? So how does chaos show up? So an immediate guess, if I add some interactions with strength j, and compute this chaos exponent, we start at chaos 0. We expect to just start going up as soon as we introduce interactions. This is not always the case. In particular, there's this idea where we start with an integrable system and we deform away from integrability. That's some small deformation. The system is not integrable anymore, but it is very, very close to being still integrable. So it's almost integrable. In particular, integrability means the theory is non-chaotic. So integrability plus a small deformation stays non-chaotic in some sense. So this idea has many concrete realizations. Two concrete realizations are KAM theory. So the KAM theorem is a very precise, rigorous mathematical theorem, which tells you exactly how much of a deformation you need in order to be completely non-integrable. Just remove integrability. Another example is the Fermi Ulam problem, which is the same idea, except that for this, you can take an integral system with an infinite number of degrees of freedom, and still you see this schematic behavior. So no chaos plus a small deformation still stays no chaos in some sense.
Sorry, I thought the number 2 wasn't it that they added some exponential potentials and the system remained integrable?
We added nonlinearities and it stays integral. Yes.
Yes, but it was just because they choose a very special potential. They chose a very special potential that made the system integral.
I thought they added, they took harmonic oscillators with x squared, they added x cubed terms.
Okay.
This is what they added.
Okay,
I don't think there's something.
Okay, maybe I'm wrong.
So the question is what happens for quantum systems now. So we start with a quantum system that is not integrable but non-chaotic in some sense. We add interactions and we ask how does chaos show up? And whether interesting behaviors also happen on the quantum mechanical level.
Sorry, question. What do you mean with almost integrable in terms of the picture on the left?
This is very precise. They have an exact definition. What I mean is that in an integrable system, you have these invariant tori in the phase space and so on. So even though I broke integrability, most of these tori remain there, even though the system is not integrable. So the phase space is still periodic in most of the phase space. Okay. And again, this is very, I'm being very schematic here, but this is an extremely precise idea. Good, so now we'll talk about quantum chaos. I have to tell you how I measure quantum chaos. I'm going to be using the OCHOP, the out of time ordered orbit. Specifically, this OTOP C is defined as taking a double commutator and taking its expectation value at finite temperature T. Some normalization, it's unimportant. Where these W and B are generic operators in my system. This is called out of time order because the times here do not appear in increasing order. And you can sort of see why this should be related to chaos. Because of this commutator in one order, first we have to be at time 0 and change the conditions. Then we measure W. And in the other order, we do it the opposite way. So this is like this changing of initial conditions and measuring what happens at large times. In systems with a large n number of degrees of freedom, we expect this outcome to behave like 1 minus 1 over m e to the lambda f of t. If this happens, we call this the chaos exponent. Again, in analogy with what happens in classical systems, this just tells us the correlations die off exponentially fast, which is what we'd expect of a chaotic system.
Is this the formula for the commutator or the OTOC?
It won't matter for microsystems. It's going to be basically the same. Why?
No, because I thought the commutator grows.
Sorry?
I thought the commutator grows with them. Or
Yeah, it's this term.
okay.
Yeah, I'm looking at the OTOC, which is going to have this 1 minus as well. Good. So what we'd like to do is measure this lambda L as a function of some parameter from weak coupling to strong coupling, and to see how lambda L grows as we introduce interactions. I'm going to mention some facts about this lambda L. So first of all, there is the lambda sandwiching to Stanford bound, which tells us that lambda L is always smaller than 2 pi over beta, with beta the inverse temperature. Specifically in this talk, we're going to talk only about scale invariant theories, and so beta is going to be the only scale in the problem. So I'm going to be setting beta equals 2 pi, and it's easy to restore it, which makes this bound just lambda L smaller than 1. Okay, so now to explain how I compute the chaos exponent generically. So there's a standard method for computing the chaos exponent in theories which have 3 assumptions, which obey 3 assumptions. So first, we assume a large n limit. We assume disorder in the sense that I'm going to explain. And we assume that the theory is scale invariant. So let me give some examples of theories which obey these 3 assumptions. First of all, we have the Syk model. This means taking n 3 fermions in quantum mechanics and having this interaction. So it's easy to see that this has a large n limit. They just take the number of fermions to be very large. This has disorder in the sense that these couplings I take to be randomly distributed with a Gaussian distribution. So the second moment is something like j squared over n q minus 1, and all higher moments vanish. This j is going to be some parameter of my distribution. And it's been shown that at j equals infinity, when this j goes to infinity, the theory has scale invariance. Or at least some correlators have scale invariance. So j equals infinity, we have these 3 assumptions, and so we can compute the chaos exponent, and we find that it is maximal. We're going to review this computation in a second. Another example, this time in 1 + 1 dimensions, is the Mulligan-Stanford-Witten model. The idea is very similar. I take 2D n equals 1, (1) Power superfields, 5, and I take this superpotential. 1, q, 1, 5. So again, large n is obeyed. We again have disorder because we're averaging over couplings. And at j equals infinity, we have scale invariance, and you can compute the chaos exponent here as well. Scale invariance. And you find some chaos exponent which depends on q now. The maximal value is at q equals 3, and it's something like 0.6, and it gets smaller as you raise q.
Is there a spatial disorder space dependent here?
No. It is constant. These j's do not depend on positions.
So, there's some X dependence to the whole correlation function.
Yes.
Okay.
I'm actually confused because if you compactify on a circle to make it, if you don't compactify on a circle, it's like having n be infinity. If you do compactify on a circle, that violates your assumption of scale invariance.
I mean scale invariance on flat space. I'm going to focus on 1 + 1, 0 + 1. I'm going to work in flat space, and conformal invariance allows me to map that to finite temperature. So all my calculations are going to be in flat space, and because I'm in d small equal to 2, I can always map that to finite temperature. Yeah.
With your butterfly velocity, just the velocity of light once you have conformal.
I'm not going to be discussing this momentum dependence, the butterfly velocity. I don't know yet what to do with it in the rest of my talk. But this has been done already for the models I've already discussed. For the ones I'm going to test talking about, I don't know yet. Great. So what we like to do is follow the chaos exponent as a function of this parameter j. For these two examples, this cannot be done because the field is always scale invariant at 2 points. J equals 0, where we have free fields, and j equals infinity, where we have some scale invariant theory. So we have the value here and the value here, but we cannot connect them because there's no scale invariance for any other j. So in order for us to be able to compute this graph, because of this crucial assumption, what we need is for j to be exactly marginal. At least the leading order in one frame. So we need a line of fixed points parameterized by this order coupling. So it's not trivial that examples where this order coupling is exactly marginal exists. We found two classes of examples where this happens. Number one is generalized free fields plus disorder. Number two is the 2D n equals 2 supersymmetric minimal models. I'm going to go through both of these tests as examples in detail. I should mention these types of graphs have been computed before in some methods. Douglas Stanford has a paper which does for the fourth matrix theory. And what he finds is continuous transition. So he finds this graph. Large Q and S by K can also compute this, and you get this graph. And there's a chiral version of this by K model done by people here at Princeton, and they also found this continuous graph. Okay, so in order to be able to compute the chaos exponent for the theories we're interested in, I'm going to start by just explaining how you do this for the simpler examples. So we're just going to do the SYK model very quickly. So I'm going to review how to find maximum chaos in the SYK model as quickly as possible. Once again, we're taking n fermions in quantum mechanics and deforming them by this interaction. So computing the chaos exponent takes 2 steps. Step number 1 is to compute the full 2-point function. 2-point function g at leading order in 1/n. And at j equals infinity, where we have scale invariance. And step number 2 is to compute the 4-point function. Full 4-point function of this c at leading order in 1/n at j equals infinity. And from this, we can read out the chaos exponent. Right, so let's go through these steps for SYK. Step number 1 is the 2-point function. I'm going to start drawing all of the diagrams that contribute to the 2-point function at leading order in 1/n. We have this, and we have this. I'm going to be doing SYK at q equals 4, but the generalization to any q is immediate. So we have this diagram, and any other diagram is given by taking this building block and iterating it over the other propagators. So I can iterate it here, or I can iterate it here, and I can keep iterating it on and on. So we can, in principle, try to resum the series, but it's nicer to instead write a self-consistency equation for G. So we write a Schwinger-Dyson equation or a self-consistency equation for the 2-point function, which looks like this. We define sigma to be this circle where all of these lines are full propagators G, and G is now given by this plus 1 sigma insertion, 2 sigma insertions, and so on. The reason this is nice is because now we can write these equations in almost algebraic form. So this means that sigma is J squared, G to the Q minus 1. And resumming this, I find that G is 1 over 1 minus sigma. This G naught is just propagator of the free fermions, just this line. So this looks extremely simple. These aren't just algebraic equations because this equation is in momentum space, while this one is in real space, but you can still try to solve them. Numerically, people have managed to solve them almost generally, but we're going to focus on the case where J goes to infinity, where these equations simplify and we can find an exact solution. So assuming that J equals infinity, we get scalar invariance. You can guess the solution to these equations. I'm going to guess G is equal to 1 of B over X to delta, where B and delta are some numbers. Plugging that answer into the equations and neglecting this term across J because this sigma term is going to win over this thing in the infrared. So we plug that in and we find some solution. B is equal to something that's not important. Delta is equal to 1 over Q. So we found the exact 2-point function at leading order 1 over n at large J. So that's step 1. Now we can do step 2 and find the 4-point function. So again, we start by writing all possible diagrams and contribute to the 4-point function. By I, sub j, sub j. At leading order, diagrams are all like this, but these are full propagators G. This is the leading term in 1 over n. But this is not what we're interested in. So remember that this 4-point function looks like 1 minus 1 over n equal to lambda of t, and we're interested in these subleading terms, 1 over n terms. So I'm going to throw away these diagrams and only focus on the 1 over n corrections. Let's look at 1 over n corrections. Again, I, J, and all of the possible diagrams look like this. We have this diagram plus this diagram plus this diagram, so on, where all of the lines are full propagators and discontinuous. So this simple form allows us to resum 4-point function and write at least a formal expression. We write it as k to the n C naught, where C naught is this initial diagram, and k is this run with the diagram. Again, this simple form allows us to write this in an algebraic way. This is resumming this as a C naught over 1 minus k. So in principle, we have the 4-point function, and now we can read off the chaos exponent from this. In fact, this is a small trick you can use to get the chaos exponent quicker. I can rewrite this equation, if I play around with this, as C equals C naught plus K times C. This is a self-consistency equation for C since it appears on both sides. And assuming that C grows exponentially time, so assuming chaos, if I plug that in here, I can neglect the C naught term. The equation becomes much simpler. The equation tells me that these types of exponential functions are eigenvalues of the kernel C with eigenvalue 1. So more generally, now to find chaos, what I do is I guess eigenfunctions of this form. The exact form is fixed by conformal invariance, but this is the only part we care about. Then I plug this into the equation k e to the lambda t. This will give me some eigenvalue that depends on lambda times the eigenfunction of f. And the specific chaos exponent that we care about, lambda L, is such that these eigenvalues are equal to 1. So finding the eigenvalues of these specific functions and setting them to 1 and get the chaos exponent for this theory. In particular, for SYK, people have done this for us. People have computed these eigenvalues. I don't remember this by heart, though. This is gamma of 3 minus 2 delta, gamma of 2 delta plus lambda, gamma of 1 plus 2 delta, 2 minus 2 delta plus lambda, where delta is still 1 over q. Setting this to 1, we find that chaos exponent is equal to 1 for any q. Excellent. So now we know how to compute chaos exponents in disordered systems. What we want to do now is to redo this calculation, but for the systems that we care about. So these systems where disorder is an exactly modular deformation. So I'm going to start by talking about this first class of example, which is generalized free fields.
Sorry, I think I missed one step. Where did you use the 2-point function in this to find lambda?
Yeah, this kernel thing is defined by the full 2-point function. So I have to find them first. Okay, so let's write down the model. And we're going to discuss 2 types of these theories, and 0 plus 1d and then 1 plus 1d. I'm going to focus on this quantum mechanical case because this one's simpler. So the theory we write down is very similar to SYK, J I1 Q, psi I1. So psi IQ. Except this time, I am setting the dimension of these fermions to be whatever I want, and I'm choosing them to be 1 over q. So a single theory with just this dimension is called a generalized free fermion. It is a non-interacting theory. It is also non-local because it doesn't have an energy momentum tensor, because I've set this to be 1 over q instead of the standard, which should have been 0 if this was an actual free fermion. But we can still think of this as a toy model where we can do computations. This model was first written down by Wallace and Waterhouse. So the reason I'm choosing the dimension to be 1 over q is because this interaction is now classically marginal. It has a direct dimension to be classically marginal. And these guys provided evidence that it's actually an exactly marginal deformation. So J is exactly marginal. Basically, they computed the 2 and 4-point functions and showed that there's no counter terms you need to add, no divergences. So the theory is just scale invariant. Good. So now we can repeat the computation of the chaos exponent for this model. Now we can do it at any j, because we always have scale invariance. So to find the chaos exponent, we have 2 steps. Step number 1 is a 2-point function. Step number 2 is the 4-point function. So let's start with step number 1. So again, we're going to draw all of the diagrams that contribute to this 2-point function. And the diagrams are exactly the same. The only difference is what I mean by this line. So this line is now a propagator for this generalized free fermion instead of the free fermion we had before. So it's something like x to the 2 delta instead of what happens when you just take this dimension to be 0. So because the diagrams are the same, the Schwinder-Dyson equations are also exactly the same. We define sigma to be j squared to be 1. We define d to be 1 over g naught minus 1 times sigma. These are exactly the same equations, and the only difference is this bare propagator. It's now the propagator for a generalized free fermion. Now we can solve these equations, but this time we solve them for any value of j. So we're going to guess a scale invariant solution for any value of j. We're going to guess that only this number depends on j, and the dimension does not. You plug that into the equations. This time you do not neglect this because you're not taking the IR limit, you're not taking this for infinity. You can still solve this with this term still there, and you find some solution. D is something, and delta is still always 1 over q. And not good, so now we do step number 2. with the 4-point function. Again, since we have generalized free fields, the diagrams are identical. We have this, so on, where all of these are the four propagators G. And so again, we have this ladder structure with the kernel equal to the same thing as before. G, G, G. And to find chaos, we want to diagonalize whatever this is and find the eigenvalues and set them to 1. So this is easy to do. Note that the 2-point function for the generalized free fields that we found over there is exactly the same as the one for SYK, up to an overall factor that we call V of J. Since the kernel is a product of 2-point functions, it is also the same as in SYK. Again, up to some overall factor. This time it's b to the power of q because we have q of these propagators. And so the eigenvalues for generalized free fields are exactly the same as the eigenvalues for SYK up to an overall function. This we know, we wrote it down before. This we know, and so we now have the full eigenvalues. So we set this to be equal to 1. And the solution gives us a chaos exponent. So let me plot the result. As a function of j, we can compute this lambda L as a solution to this equation, and this is what we find. So there are two interesting sides of this graph. We'll solve that large j. As j goes to infinity, the chaos exponent approaches 1. This makes sense because there's some intuition that this generalized free field model, when you take j to infinity, it goes to the same fixed point as the usual SYK model. So it doesn't matter what model you started off with, the CFT at the end is the same. Clearly, the more interesting case is this side of the graph, where the chaos exponent becomes negative. So we need some interpretation of this side. So negative chaos doesn't really make sense intuitively. And indeed, in getting the chaos exponent, we made some approximations that we have to go back and check now. So we computed this 4-point function from this equation. What we did was we assumed positive chaos that allowed us to neglect this term, and then we got the eigenvalue equation. And now we have to go back and reintroduce this because we did not find positive chaos. So clearly this side, our approximations when we got here are just inconsistent. So this does not make sense. What we can still say is that we assume positive chaos and did not find any solutions to positive chaos. So the correct interpretation is that this stays 0 because there's no chaos in this region before it starts going up. So what we found is that you need to go a finite distance away from these generalized free fields in order to start seeing chaos in these models. So this is like a quantum version of this KAM. In the sense that the theory stays non-chaotic for a finite deformation away from our initial system.
Sorry, maybe naive, but the negative Lyapunov exponent makes sense. But
What do you, in general? I don't know. In this case, no. Because we made approximations, we assumed positive chaos in doing this computation.
okay.
So
So
getting
it's not
negative
large.
just means our approximations were inconsistent.
Sorry.
In general, I don't think it makes sense, but maybe you can cook up some system where if this is the leading contribution, then there's no other things, and maybe this is okay. Okay, so what, yes.
But if you go back to the equation you've written there, C equals C naught plus K C, maybe it will show slower growth of the OTOG for large T.
That means there could be polynomial growth or other things here as well. That's why negative chaos, I don't take it seriously.
I know, but I wonder if you determine what does happen.
I'm not sure. I don't know the answer to this. Now, part of my problem is I'm not sure if at leading go to 1 over n the question makes sense.
Well, your equation makes sense. It will determine something for the 4-point function.
Time scales. Right, so when I assume this exponential growth, I'm always looking at specific time scales between this log n and over 1. once it's not exponentially grown, it's polynomials. I'm not sure this is the correct timescale to be thinking about it.
Whatever the equation is, it'd be interesting, and we valid under sometimes.
Okay. I don't know what the answer is, what actually happens. Regardless if I define this to be my chaos exponent, then it is zero. Our polynomial growth, I define it to have zero chaos exponent. But I don't know what the actual answer is.
Would it be of order 1 over n?
Yes, I don't know how to define this.
Because I thought in some examples it is of order 1.
Yeah, in the ON models, people computed to be 1 over n, but this is kind of, it's a little different because your coupling is like 1 over n. So it's like finding a small, this is like seeing this continuous graph as a function of your coupling. In general, I'm not sure how to define chaos at subleading order 1 over n. But yes, at subleading order, you're going to see some contribution that is either very small here, and this also makes the transition smooth probably, instead of having this jump. Right, so let's look at what happened and what led to this continuous transition into chaos. So we have this equation for the eigenvalues, which I'm going to repeat. Eigenvalues for generalized fields, some function times the eigenvalues for SY. In the limit j goes to 0, we're on this side of the graph. This coefficient vanishes. This makes sense because all of my interactions vanish, so I don't expect a kernel. But because we want to set this to 1 for any value of j, if this vanishes, that means that we need this to diverge. The values of lambda which give us chaos in the limit j goes to 0 are obtained by looking at this and asking where it diverges. So lambda L is such that chaos by k diverges. And this is a general result because in any theory, we expect these eigenvalues to go to 0 as j goes to 0, unless we also take some double scaling limit with this lambda approaching some diverging value, such that together they conspire to get this to be equal to 1. So in the general system, in order to find chaos at small j, we've learned that we need to look for lambda L such that this thing diverges at finite with small j. So at small j, we look for divergences of these eigenvalues. Okay, at small with finite. Okay, excellent. Now I'm going to move on to the second class of examples. The second class of examples is the supersymmetric minimal models. So to explain these models, we'll start with a small toy example. Let's discuss the XYZ model.
Let me ask you a question before you continue.
Sure, yeah.
So there is this qualitative explanation for chaos that involves that when you act with the interaction, the operator splits into 3 operator or Q minus 1 operators, and then each one splits and so on, and creates these 3 growing operators. And it would seem to me that that explanation should also qualitatively hold for the for this case.
And asking what goes wrong.
Yeah. So is there a qualitative explanation here?
I don't know the answer to this. I don't know the answer to this. More generally, I mean, these types of graphs, I don't even understand how to explain them intuitively, even classically. And I've seen these graphs even classically. The K-Theorem theorem, in some cases, predicts these graphs. I don't understand them. I don't know how you explain intuitively that chaos doesn't just immediately show up. I think this is part of what makes this such a strong result classically. I mean, not our result. So I don't have any intuition for how you don't just get chaos.
Do you have a classical system in mind that looks like this?
Yes.
You can come back to it later. then.
No, it's 5 seconds. You take 3 masses and connect them with springs whose stress lengths are L0, which is not 0. And now so this has some rest configuration like this, and now you sort of take this one over here and you see what happens in the system. So if you have small deformations, the theory is basically integrable. I mean, it is integrable. So for small deformations, let's say I have some energy E, which tells me how big the deformation is. For small energies, this is integrable. But for large enough deformations, it is unchaotic. And this was studied numerically, and they computed the chaos exponents. The average chaos exponent on the phase space, and you see exactly this. It's basically 0 here, and then it starts going up at some point. So because it's numerically, it's not exactly 0, but it's just, there's a very clear phase transition between almost 0 and then suddenly starts shooting up.
Those springs must be nonlinear.
The rest length is non-zero, yes.
But they could still be harmonic. You must have a non-linear force, don't you? All right, don't worry.
No, I'm sorry, we're over here. Right, okay, so before discussing the minimal models, when we apply model, it's called the XYZ model. I take 3 chiral superfields, so 2D n equals 2 chiral superfields X, Y, and Z. Let's discuss this superfield. G, X, Y, Z, plus tau, X2, Q. There's a standard argument due to the image transfer, which is used to show that there is a component manifold in the space of G and tau. So G and tau are 2 complex parameters. There's one complex dimensional component manifold in this space. Basically, what you do is using supersymmetry, you show the beta functions for these 2 are linearly dependent, and so there should be one complex dimensional line of solution to this space. So I want to access the same component manifold in this G tau space from a different perspective to make it easier to generalize this to an SYK-like model. So now we're writing down the same conformal manifold from a different perspective. So first I will discuss what happens if I just take an x cubed. This is known to flow to something called the n equals 2 supersymmetric A2 minimal model. And the fact about this minimal model is that in its spectrum, there's a chiral operator, which I will call x tilde, such that its dimension is 1/3. It's just set by the superposition, basically. So I will take 3 copies of this model. Q plus y cubed plus z cubed. So what we've done is we've gone to 3 copies of this A2 minimum model. Now we can think of deforming this model in conformal perturbation theory. So around this model, now adding this deformation. X tilde, y tilde, z tilde. So the picture is I start in the UV with X, Y, and Z, which are 3 superfields. I've gone to 3 copies of the A2 minimum model, and now I add this small deformation J. This is classically modular by construction because the dimension of each one of these is 1/3. And because there are no global symmetries to this model, to this 3 copies of the A2 minimum model, this has to be an exactly modular deformation. So this is a result due to Seiberg, Komogolski, Fujikawa, Green and Webb, and also again, the statement is take a 2D n equals 2 supercomponent field theory with no global symmetries, which are not all symmetries, no global sims. Then any classically modular deformation is automatically exactly modular. So this deformation just takes us along the same conformal manifold that we saw in the UV. But now we know exactly the form of this exactly marginal information. And in conformal motivation theory, we can do computations using this form. So now I want to write down a more general form for this model. So let's start by discussing a single Carroll superfield with superpotential pi to the q. This is known to flow to something called the n equals 2 supersymmetric AQ minus 1 minimal model. Some facts about this minimal model. First, it has a chiral operator phi tilde in a spectrum with dimension 1 over q, again just set by the superpotential. The central charge is 3 times 1 minus 2 over q, and it has no global symmetries, continuous non-R symmetries. So now we can just repeat this construction. We take n copies of this minimal model. So this just gives me n copies of the q minus 1 minimal model, and I deform by j I1, by q, by tilde I1, by tilde I2. So by this same argument, what we learn is that every realization of these j's, every value is a CFT. I should say that here I'm taking I1 not equal to I2. So every realization is a CFT even before I average. Because these dimensions of the phi tildes are fixed, so the dimension in any CFT of a chiral operator is always fixed, be this 1 over q due to the R symmetry. When I average, I also expect to see a conformal invariant correlator, right? So let's look at the 2-point function, for example. Phi tilde bar. For a generic value of these j's, this is some function of the j's over x to this power. Now, when I average, since this does not depend on j, what I get is that on average, I'm going to get some number over x to delta. And so it also has a scale invariant form. This is also true for higher endpoint functions. And so I expect that even on average, correlators here will have the scale invariant form I'm looking for. And so when I average, j should be an exactly marginal operator. So we can try to redo the computation for the chaos exponent as a function of j in this model and see what we get.
Again, the disorder is independent of position.
Yeah, yes, it's
Independent of time.
independent. It's numbers, it's constant numbers.
Okay, all right.
Okay, so we know how to compute chaos exponent.
Chiral, is that right?
No, not chiral.
Okay.
What do you mean by chiral?
The correlation will depend on x plus I tau.
No. It's not chiral. I meant when I said chiral superfields, they're not being chiral in the fermion sense, in the supersymmetric sense. Good. So we have two steps to compute the chaos exponent. We have the 2-point function and the 4-point function. But this time the computation is much more difficult. Let's start drawing diagrams to contribute to the 2-point function. We have the same diagrams we had up to now. But what we're doing now is expanding around these non-trivial CFTs and not around the free theory. So the theory without this deformation already has a non-trivial 4-point and 6-point and 8-point function. So those other diagrams that contribute at the same order in 1 over n. For example, I can write this diagram. So what I've done is I'm using the 6-point function of the minimal models and the 4-point function. And if you go through the large n combinatorics, you see that this contributes to the same order as this diagram, for example. And in general, any endpoint function of this CFT is going to contribute to G at some order in perturbation theory. So in order to compute the 2-point function, we need some new mechanism. So luckily for us, it turns out that there's also a self-consistency equation you can write down when you expand using this disordered information around the general CFT, which includes all of the endpoint functions of the CFT. I'm going to write down the form of this expression that we found. So we still define sigma to be the same thing. This is G, 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 and now G is slightly more complicated. It's this plus this, this, so on. So we should define what 4s and 6s are. So an NS correlation function is a subtracted endpoint function. What I mean is I take the endpoint function, there's a specific subtraction I have to take in order to get this. So for example, 4s is always defined for any CFT as the FourPoint function minus this product of propagators. More generally, with an algorithm to get any NS point function at any order, the basic idea is you plug in what you would have plugged in for free theory. For example, the FourPoint function is just some combination of propagators. You plug this in, and you find out that some of these contributions are disconnected. So if I plugged in this contribution here, I would have found this diagram. So I remove this contribution ahead of time, and that gives me this subtract the 4-point function. And now this is true for any CFT. So for any CFT, I just plug in this. And a similar algorithm gives you the 6-point function, the 8-point function, and so on. So I'm going to tell you that you can actually prove, we prove this from the Dyson equations in the same sense that you can prove them around a free theory by using the G sigma formalism. So this looks very complicated because you need all endpoint functions of the CFT. But note that in perturbation theory in J, you only need the first few endpoint functions. So in order J squared, you only need these two diagrams. So you only need the 4-point function. At order J to the 4th, you only need these three expressions, so you only need the 4 and 6-point functions. And so on.
Is known, the 4-point function, 6-point function. These are known in this model. But
the 4-point functions are known in general. How endpoint functions are not known. I'm going to reduce to an example where we know all endpoint functions in a second. So perturbation theory is still valid, it's still doable. Good, so we know the 2-point function at least in principle. Now we need the 4-point function. So around the free theory, we have this ladder structure. And it turns out that around the non-trivial CFT, again, we find the ladder structure. So again, we find this is given by some sum to infinity, k to the n and C naught. This time C naught is again more complicated. And the kernel is also more complicated.
You're a large n limit here or no?
I'm only getting more than 1 over n. So yes,
What is the n here?
the number of chiral superfields I have, or the number of minimal models I'm expanding around. So again, this is very complicated. It looks like you need all endpoint functions. First, let's define these NS primes. They have a very similar definition. For example, the 4s prime is just a different subtracted endpoint function. It's the 4-point function minus this combination of propagators. And in general, the idea is the same. You plug in the free result for the 4-point function and you subtract disconnected contributions. Once again, it looks like you need all endpoint functions, but in perturbation theory, you only need the first few. So the leading order term at J squared is just this term, and then you need this one the next order, and so on. Well, this looks complicated just because we know that we have a kernel immediately allows us to compute the chaos exponent by diagonalizing it. So even though it's complicated, now the question is well defined. We diagonalize this kernel, we find the eigenvalues, maybe in perturbation theory in J. We set them to 1, and we should find what the chaos exponent is. Good. So now let's try to do this for our minimal models. So we're going to focus on a specific case, which is Q equals 3. The reason I'm doing this is because this model is simpler than the others. I'm going to write down explicitly the superpotential. This is sum by I cubed plus j I j k I j k. So this theory without deformation is n copies of the A2 minimal model, but the A2 minimal model has central charge 1. So A2 has central charge 1, and so it is equivalent to the theory of a free compact boson. It is a free theory. So we have some compact boson. And indeed, there's a specific value of this radius r where the free compact boson is known to have n equals 2 supersymmetry. So r equals square root of 3, square root of 3 over 2, and the T dual versions have n equals 2 supersymmetry. And so this A2 minimal model flows to one of these radii. It's not important for our purposes which one. What this means is that my operator phi tilde, which is some chiral operator in a single copy of these A2 minimal models, should correspond to some vertex operators in the free boson CFT. So let's write this down in components. This should have dimension 1/3. This should have dimension 4/3, and so on. So I have to check that this free boson CFT at this radius has vertex operators with the correct dimensions for these 3 fields, and indeed it does. So I find vertex operators correspond to these 3 fields. What that means is now I know all endpoint functions of this phi tilde. I know all endpoint functions of vertex operators, so I know all endpoint functions of the components. So I immediately know any endpoint function of phi tilde. This is some combination of correlators of vertex operators. So I can take this result and plug this in here and try to read off the chaos exponents. So let's do the leading term. The leading term in small j is given just by this diagram. So I'm going to draw it again. Leading order in j squared, we just have this diagram. I know what this 4-point function is now because I know phi tilde in terms of these vertex operators. So I can write this down and I can look at the eigenvalues at leading order in j squared. Eigenvalues k lambda at leading order in j squared. And I can use this to read out the chaos exponent at small j. What we find is that at small j, when the limit j goes to 0, the chaos exponent is 0 and not negative like in the general 3 fields. What that means is that now we should get a continuous transition. Something like this, a continuous transition to chaos, and another discontinuous one.
Go back to this equation you had for lambda for little k. Is that being evaluated at 0 external momentum? Yeah, so there's an issue there pointed out paper by Gu and Katev a couple of years ago, where they show that when you integrate over momentum, you get additional poles in the 4-point correlation function that in fact push the value of lambda back up to 1.
In which model?
For all models, it's a very general sort of.
This is not the pole skipping problem.
No. This is Gu and Katev. They're looking at any model which has a ladder type summation, which seems to be yours, and also a spatial structure. And they prove something called a ladder identity, which allows them to show that in the imaginary momentum plane, Along the imaginary momentum axis, there's a pole. And if you include the contribution of the pole, the actual, under certain conditions, the actual Lyapunov exponent is exactly 2.
So whenever I have this ladder structure, it's always equal to 1.
Sorry?
Whenever I have a ladder structure, it's always equal to 1.
If the pole dominates, it may not dominate against the
I see.
contribution here. So there's some subtle criterion you have to check.
Okay.
Yeah, so you look into that, I think.
Right, let me summarize and tell you about some small coincidence that we're looking into. So we looked at 2 classes of examples where this order is exactly marginal. The first one was generalized free fields. That's this order. The second one was the 2D supersymmetric minimum models plus this order. In this theory, we found a discontinuous transition into chaos. But in this theory, we found a continuous transition. So this seems to hint at some quantum mechanical conversion of the KAM theory. Along the way, in order to compute the chaos exponent for this theory, which is a non-trivial CFT, we had to write down new versions of these Schwinger-Dyson equations for the 2-point function and the kernel structure for the 4-point function, which are now valid around any non-trivial CFT, not just around free theory. I want to end by discussing some coincidence that we're looking into. So when we wrote down the 4-point function, we had this equation. So this came from this kernel structure, and this was just that j equals 0. This is the j equals 0 contribution. So far, we ignored this term. Just threw this out and looked at only contributions from this term. Now we have to go back and make sure that this isn't, this doesn't dominate. This doesn't give us a larger chaos exponent. So what we can do is take the chaos exponent we computed here and take the limit j goes to 0 and compare it to the chaos exponent this gives us. And what we find is that in both of the examples we found, so both in the minimal models and in generalized free fields, these two exactly match at j equals 0. So the minimal models are both 0, the generalized free fields are both negative at the same value of -2/p. What this means is that in order to find the chaos exponent at j equals 0, it's enough to know a single copy of the CFT, because here the theory is all decoupled. So it's enough to just take a single copy of the CFT and compute this, which is just some certain limit of the 4-point function, in order to read out the chaos exponent. So if around the general CFT, these two things match, the chaos exponent from the kernel and from the C0, they match, then in order to know whether the transition is continuous or not, you just have to compute this at j equals to 0 and see whether or not it's negative. If this is negative, then you have this discontinuous transition. If it's positive or 0, you have a continuous transition. So if this is always true, then this is the start of some quantum mechanical version of the KAM theorem, where you give me a single CFT and I tell you whether the transition to chaos is continuous or not. Thank you.
This theory with the cubic superpotential, it's basically exactly solvable at large n, right?
Without the deformation or with the deformation?
With this JIJK, phi by J phi k.
Why do you think it's solvable? I don't think it's solvable.
Well, if you, because of these sum of phi I cube. But suppose you remove these sum of phi I cube.
Yeah, at j equals 0, like without the deformation. So at j equals 0, we just had the minimal models, which are solvable. So we had this model is solvable. I don't know how to solve this additional.
We looked at the case where there is, say, if you expand around the 3 minus epsilon dimensions, there are where you don't have the initial term, but you just have the J term, and that seems solvable.
Yeah, but this is weakly coupled, right? So you're doing epsilon expansion. And the epsilon expansion, I agree.
So you can just sum it for any epsilon. Yeah, we can talk about it.
But this is like a free theory, right? You're just saying, you know.
Well, it's a type of melonic theory.
I see. I mean, it's the same form of the SYK model where you take some free theory plus this random information.
Yeah, this theory with the cubic is like Q equals 3 SYK model for boson, like bosonic type. That is solved.
You're trying looking at the epsilon expansion in the sense that you have a similar thing where in the epsilon expansion, this is going to be something like epsilon, this is going to be something like epsilon squared, and so on. And then you try to solve it in the epsilon expansion. But I'm not sure if epsilon goes to 1 if it's still solvable.
Yeah, there is a paper on this. Let me look it up.
So it's more of a curiosity. It's related to this example or this idea of the KAM theory. So if you have something for which the KAM theorem holds, so some classical system, and you just quantize it, do you get something where you have this sort of quantum chaos?
The problem is that when people say KAM theorem, they mean a very precise, rigorous mathematical theorem, which is just, I don't know how to formulate it in quantum mechanics. It's a theorem.
Have a mechanical system you can quantize, right? And try to write some
But the questions you ask, like you can't really talk about a phase space anymore in the sense that they talk about in classical mechanics. So when people ask these questions in quantum chaos, they don't mean what is the value of this Lyapunov exponent. They mean what is the structure of the phase space, are there periodic orbits and so on.
Right, but would you be able to look at things like the distribution of the spectrum or things like that, right? Supposedly there are different spectra.
For this, I don't know what the answer is. If you just take something that you'd expect the KAM theorem to apply to. So the KAM theorem, we discussed it when you start with an integral system and you deform away. I don't think this is the correct version of whatever the statement is here, because both of these theories are integrable, but only one of them displayed. Okay, this theory is integrable, and it displays a continuous transition. I'm not sure if this is integrable or not. I don't know in what sense it's integrable. It's a free theory, and it does display this continuous transition. So I don't know if integrability is what sets apart the theories with a discontinuous from a continuous transition to chaos. I don't know what physically is, what thing separates these two theories, except for saying this weird limit of the 4-point function.
But I mean, C0 looks like it's somewhat ill for the case of generalized free fields in the sense that it decreases in this chaos limit where one would expect the generic 4-point function not to decrease. I mean, just to be constant.
I don't think it's this is not an artifact of generalized free fields. There are other examples, but this is negative. I'll give 2 classes of examples. So the 2D minimal models without SUSY have negative whatever this is, and the 3D Ising model. This was done in a paper by Simone Cohen-Wall with 2 other people. Also has a negative value of this. I can't call it the chaos exponent, but whatever this is, it is also negative in these 2 examples. So if you can build a conformal manifold in a similar way, in the similar structure that I did around these theories, around n copies of these theories, I also expect this discontinuous transition. And at least for this case, it should be possible. I don't know about this case. So I don't think it's an artifact of taking generalized free fields.
Sorry, it's another probably naive question, but I understand you can't compute this for SYK, but readily accessible.
The middle, yes.
Lambda it's just like the continuous one.
I don't know what happens for SYK in these intermediate scales.
It's not known.
Maybe someone used the memory. I don't
Yeah,
know.
that's
I don't know the answer.
Okay.
Actually. I'm not sure.
Is this chaos exponent always monotonic? Yes.
The examples we looked at, and generally you would expect this to be the case, right? If the interactions are stronger, you expect more chaos. But I don't know of any proof this is the case. We haven't seen a counterexample.
But couldn't it like flow to some other fixed point? Like, okay, maybe it's not exactly marginal.
It could. Yes. I would like to see an example where this happens. I don't have one.
Okay, there are no more questions. Let's thank Adar again.